Tonight we're leaving Earth behind completely. We're journeying to a place so distant that the light we see from it tonight began its voyage before humans even existed. We're heading to the Andromeda Galaxy, our cosmic neighbour, our future collision partner, and one of the most mysterious objects in the night sky. So before we begin this journey together, if you enjoy these deep dives into the cosmos, go ahead and hit that like button and subscribe to the channel. And as always, let me know in the comments where you're watching from tonight and what time it is in your corner of the world. Now get comfortable, maybe dim the lights, turn on a fan for that gentle background hum, and let's drift into the darkness together. Let's explore the real secrets of the Andromeda Galaxy. On a clear autumn night, far from city lights, you can see something extraordinary with your naked eye. Look northeast from the Great Square of Pegasus, and there, hanging in the darkness like a faint smudge of light, is the most distant object visible to the unaided human eye. A pale, elongated blur, roughly 6 times the width of the full moon in apparent size, though so faint that most people never notice it. This ghostly apparition is the Andromeda Galaxy. The light entering your eyes at this very moment left that galaxy 2.5 million years ago. When that light began its journey, our earliest human ancestors were just beginning to walk upright on the African savanna. Homo habilis, one of our earliest predecessors, was crafting the first crude stone tools. The light travelled through the vast emptiness of intergalactic space while entire species rose and fell on Earth, while continents shifted, while ice ages came and went. And now, tonight, that ancient light completes its journey by entering your eye. This is Andromeda, the nearest large galaxy to our own Milky Way. A vast spiral of hundreds of billions of stars stretching across 152,000 light-years of space. A universe unto itself containing more stars than there are grains of sand on all the beaches of Earth. And yet, despite its incomprehensible scale and distance, Andromeda is practically in our cosmic backyard. In the grand scheme of the universe, where galaxies are measured in billions of light-years away, Andromeda sits just 2.5 million light-years from us, close enough to see with our eyes, close enough to study in exquisite detail, close enough that, in a few billion years, it will collide with us. But Andromeda is more than just our nearest large neighbour. It's a cosmic Rosetta Stone, a laboratory where we can study galaxy formation, evolution, stellar birth and death, dark matter distribution, and the violent history of galactic cannibalism. Because unlike our own Milky Way, which we observe from the inside surrounded by obscuring dust, and unable to see the forest for the trees, Andromeda we see from the outside. We have a god's eye view of this magnificent spiral galaxy. We can map its structure, count its stars, trace its spiral arms, measure its rotation, and piece together its violent past. Every secret we unlock about Andromeda teaches us something about galaxies in general, including our own. The galaxy we see tonight, that faint smudge in the autumn sky, is actually just the bright central core. The full extent of Andromeda, if our eyes could see it, would dominate the night sky. The galaxy's true size, including its faint outer regions and stellar halo, would appear larger than the constellation Orion. Imagine that. A galaxy so vast that if we could see all of it, it would stretch across a significant portion of the sky. But our eyes aren't sensitive enough. We see only the bright heart of this cosmic behemoth. For most of human history, Andromeda was a mystery. Ancient observers saw it as a little cloud, a nebulous patch among the stars. They had no idea what they were looking at. No concept that this faint blur was another galaxy, another island universe containing hundreds of billions of stars. To them, it was simply a curious feature of the night sky, perhaps a hole in the celestial sphere, perhaps a distant swarm of something unknown. The first written record of Andromeda comes from the year 964, when the Persian astronomer Abd al-Rahman al-Sufi described it in his Book of Fixed Stars as a small cloud. But surely others had seen it before. Any human with good eyesight in a dark sky location would have noticed this pale smudge. It was there in the sky when ancient civilizations built their monuments. It was there when the pyramids were constructed. It was there during the rise and fall of empires, always watching, always present, always mysterious. For over 1,000 years after Al-Sufi's description, Andromeda remained an enigma. Astronomers catalogued it, observed it, drew it, but didn't understand it. In 1764, Charles Messier included it as the 31st object in his famous catalogue of fuzzy things that weren't comets. Thus, it became Messier 31, or M31, the designation still used today. Later, it would also receive the catalogue number NGC 224 in the new general catalogue, but a name didn't bring understanding. What was this nebulous object? Was it a cloud of gas within our own cosmic neighbourhood? A cluster of unresolved stars? Something else entirely? The telescopes of the 18th and 19th centuries revealed more details but brought more questions. William Herschel, the great astronomer who discovered Uranus, observed a faint reddish hue in Andromeda's core in 1785. He believed it was the nearest of the great nebulae, but he wildly underestimated its distance, thinking it was no more than 18,000 light-years away. In 1850, William Parsons, the 3rd Earl of Rosse, made a drawing that showed Andromeda's spiral structure for the first time. Suddenly this nebula had structure, form, complexity. It wasn't just a formless cloud, it was organised, deliberate, like a cosmic whirlpool frozen in space. In 1864, William Huggins examined Andromeda's spectrum and made a crucial discovery. Unlike gaseous nebulae, which showed distinct emission lines, Andromeda showed a continuous spectrum similar to starlight. This suggested that Andromeda was not simply a gas cloud. It was made of stars, countless stars so distant and numerous that they blurred together into a faint glow. But were these stars within our galaxy? Or could this spiral nebula be something else? Something far more profound? The early 20th century brought the Great Debate, a pivotal moment in astronomical history. On one side stood Harlow Shapley of Harvard, arguing that the universe consisted of a single galaxy, our Milky Way, and that spiral nebulae like Andromeda were simply features within it. On the other side stood Heber Curtis, who proposed that these spiral nebulae were actually separate island universes, galaxies in their own right, scattered throughout a much larger cosmos. The debate raged, evidence was presented, arguments were made, but the truth remained elusive. The distances involved were simply too vast to measure with the technology of the time. Then came Edwin Hubble. Using the massive 100-inch telescope at Mount Wilson Observatory in California, Hubble discovered something revolutionary in 1923. He identified a Cepheid variable star in Andromeda. These special stars pulse with a regular rhythm, and their period of pulsation is directly related to their intrinsic brightness. By measuring how bright the star appeared to be, and comparing it to how bright it should be based on its pulsation period, Hubble could calculate the distance. The math was irrefutable. Andromeda was approximately 900,000 light-years away, far, far beyond the boundaries of the Milky Way. Andromeda was another galaxy, a separate island universe, and if Andromeda was a galaxy, then so were the other spiral nebulae scattered across the sky. Overnight, the known universe expanded from a single galaxy to countless galaxies stretching into infinity. It was one of the most profound discoveries in human history. We were not alone in a single galaxy. We inhabited a cosmos filled with galaxies, each containing billions of stars, each separated by vast gulfs of empty space. Hubble's initial distance estimate was wrong. He wasn't aware that there are two types of Cepheid variables with different brightness relationships. When this was discovered in 1953 using the new 200-inch telescope at Palomar Observatory, Andromeda's distance was revised. It wasn't 900,000 light-years away, it was more than 2 million light-years away, more than twice as far as initially thought. The universe, already vast beyond comprehension, had just doubled in size again, and Andromeda, our cosmic neighbour, was even more distant and even more magnificent than we had imagined. Today, modern measurements place Andromeda at approximately 2.54 million light-years from Earth. That's roughly 24 quintillion kilometres, or if you prefer, about 15 quintillion miles. To put that in perspective, if you could travel at the speed of light, covering 300,000 kilometres every second, it would still take you 2.5 million years to reach Andromeda. Light itself, the fastest thing in the universe, takes that long to cross the gulf between our galaxies. And yet, in cosmic terms, Andromeda is right next door. Most galaxies we observe are billions of light-years away, existing in a universe so remote that the light we see from them began its journey when the universe itself was young. Andromeda is local. It's part of our cosmic neighbourhood, the Local Group, a collection of more than 50 galaxies bound together by gravity. So what exactly are we looking at when we gaze at Andromeda? We're seeing a barred spiral galaxy, similar in structure to our own Milky Way but larger. Andromeda's disk stretches approximately 152,000 light-years from edge to edge, making it the largest galaxy in our local group. Our Milky Way, by comparison, is about 100,000 to 120,000 light-years across. Andromeda is bigger, more massive in terms of stellar content, and contains an estimated 1 trillion stars. 1 trillion. That's roughly 3 times the stellar population of the Milky Way. Each of those trillion stars is a sun in its own right. Many of them have planets. Some of those planets might harbour life. There could be civilizations in Andromeda looking back at us right now, seeing our Milky Way as we see their Andromeda, a faint smudge in their night sky. The galaxy's structure is breathtaking. At its heart lies a supermassive black hole, a monster containing about 100 to 140 million times the mass of our Sun, compressed into a region smaller than our solar system. Around this dark heart swirls a dense nuclear star cluster, packed with millions of old stars orbiting in chaotic trajectories. Moving outward, we encounter the bulge, a roughly spherical collection of older yellowish stars that formed early in the galaxy's history. These stars have been orbiting the galactic centre for billions of years, their light now reddened with age. Beyond the bulge spreads the disk, a vast, flat structure containing most of Andromeda's stars, gas, and dust. The disk is where the action happens. Here, massive clouds of hydrogen gas collapse under their own gravity, igniting into new stars. These newborn stars, hot and blue, blaze with fierce light, illuminating the gas around them and creating glowing nebulum visible across intergalactic distances. The disk is also home to Andromeda's spiral arms, those elegant structures that give spiral galaxies their name. The arms aren't solid structures, but rather density waves, traffic jams of stars and gas moving through the disk. As material enters an arm, it slows down and compresses, triggering star formation. Bright young stars light up the arms, making them stand out against the darker interarm regions. But Andromeda's disk is oddly lopsided. The galaxy appears to have multiple spiral arms, but they're not symmetrical. One side of the disk is more prominent than the other. There are dark dust lanes snaking through the arms, blocking the light of stars behind them. There are bright clusters of young stars scattered throughout. And there are peculiar features, structures that don't quite fit the standard model of a pristine spiral galaxy. These oddities are clues, evidence of a violent past, signs that Andromeda hasn't been peacefully rotating for billions of years. Something has disturbed it. Multiple somethings, in fact. Surrounding the visible disk is the halo, a vast, roughly spherical region extending far beyond where the spiral arms end. The halo is populated by globular clusters, dense spheres of ancient stars that formed when the galaxy was young. Andromeda has hundreds of these globular clusters, each containing hundreds of thousands to millions of stars packed into a region just tens of light-years across. the clusters orbit through the halo on elliptical paths, swooping in close to the galactic core and then sailing back out to the far reaches. Some of these clusters are among the oldest objects in the universe, their stars dating back more than 12 billion years. The halo also contains old individual stars scattered thinly through space. These halo stars are the orphans and refugees of Andromeda's violent past. They're the remnants of smaller galaxies that Andromeda consumed long ago. Their parent galaxies ripped apart by tidal forces, and their stars scattered throughout Andromeda's halo. By studying the motions and properties of these halo stars, astronomers can reconstruct Andromeda's history, identifying where and when galactic collisions occurred. And then there's the dark matter halo, an enormous sphere of invisible matter that dwarfs everything else. Dark matter doesn't emit light. It doesn't interact with electromagnetic radiation at all. We can't see it directly. But we know it's there because of its gravitational effects. The stars in Andromeda's outer regions are moving faster than they should if only visible matter was present. Something is pulling on them, accelerating them beyond what the visible stars and gas can account for. That something is dark matter. Based on rotation curves and gravitational modelling, Andromeda's dark matter halo likely extends 200,000 light-years or more from the galactic centre and contains several times more mass than all the visible stars combined. Dark matter is the invisible scaffolding upon which Andromeda, and indeed all large galaxies, are built. The total mass of Andromeda is difficult to pin down precisely, but current estimates place it somewhere between 800 billion and 1.1 trillion solar masses. For years, astronomers thought Andromeda was significantly more massive than the Milky Way, perhaps 50% heavier. But recent studies have called this into question. More careful measurements suggest that Andromeda and the Milky Way might be roughly equal in total mass, with any difference being much smaller than previously thought. The uncertainty comes from the difficulty in measuring dark matter. We can see the stars, but the dark matter that dominates the mass budget is invisible. We must infer its presence from its gravitational effects, and those measurements come with significant uncertainties. What we can see with certainty is Andromeda's stellar population. The galaxy glows with the light of hundreds of billions of stars. In the central regions, the light has a yellowish hue, dominated by old stars that formed billions of years ago. These ancient suns have exhausted the hydrogen in their cores and have swollen into red giants, their surfaces cooled to temperatures that give them a reddish-orange colour. They're the senior citizens of the galaxy, having witnessed its entire history. Out in the spiral arms, the picture changes dramatically. Here, the light is bluish-white, dominated by massive young stars burning hydrogen at ferocious rates. These stars are short-lived cosmic beacons, shining brightly for only millions of years before exploding as supernovae. They're born in stellar nurseries, vast clouds of gas and dust where gravity pulls material together into clumps that ignite into nuclear fusion. The largest of these star-forming regions can give birth to hundreds or thousands of stars in a single event, creating open clusters that drift through the disk for hundreds of millions of years before gradually dispersing. One of the most prominent star-forming regions in Andromeda is NGC 206, a massive star cloud visible even in amateur telescopes as a bright patch along one of the galaxy's spiral arms. NGC 206 is approximately 4,000 light-years across, and contains numerous young, hot stars that illuminate the surrounding gas with ultraviolet radiation, causing it to glow in the characteristic red of ionized hydrogen. This single star cloud is larger than many dwarf galaxies. It's a stellar factory on a scale almost impossible to comprehend. The Hubble Space Telescope has revolutionized our view of Andromeda's stellar population. Over the course of more than a decade, Hubble observed the galaxy in 600 separate overlapping fields of view, building up the most detailed image ever made of another galaxy. The resulting mosaic, released in January 2025, contains 2.5 billion pixels and resolves an estimated 200 million individual stars. Each tiny point of light in the image is an entire sun, potentially with its own family of planets. The image shows stars of all ages, from ancient red giants to brilliant blue supergiants. It shows dust lanes where future stars are gestating. It shows the scars of past collisions. It shows a galaxy in all its complex chaotic glory. But even 200 million resolved stars represents just a fraction of Andromeda's total stellar population. Hubble can only see the brighter stars, those more luminous than our Sun. The vast majority of Andromeda's trillion stars are fainter red dwarfs, small cool stars that will burn for trillions of years but emit so little light that they're individually invisible from our vantage point 2.5 million light-years away. These red dwarfs vastly outnumber all other star types, making up perhaps 70 or 80% of all stars in the galaxy. They're the silent majority, the cosmic proletariat, invisible to our instruments but dominating the senses by sheer numbers. Scattered among the stars are the remnants of stellar death. When massive stars exhaust their nuclear fuel, they don't fade quietly into the night. They explode as supernovae, briefly outshining entire galaxies before leaving behind either a neutron star or a black hole. These stellar corpses litter Andromeda's disk. Astronomers have identified numerous supernova remnants, expanding shells of gas still glowing from the violence of the explosion that created them hundreds or thousands of years ago. Some of these remnants are associated with pulsars, rapidly spinning neutron stars that beam radiation into space like cosmic lighthouses. Others likely contain stellar mass black holes, the collapsed cores of the most massive stars, their gravity so intense that not even light can escape. In 1885, astronomers observed a spectacular supernova in Andromeda, designated S Andromedae. It was the first supernova ever detected outside our own galaxy, though at the time, astronomers didn't yet know Andromeda was a separate galaxy. The supernova briefly reached 6th magnitude, making it visible to the naked eye and almost as bright as Andromeda's nucleus. For a brief moment, a single dying star in a galaxy 2.5 million light-years away shone bright enough for human eyes on Earth to see it without a telescope. The explosion must have been unimaginably violent. For the star to appear that bright from such an incredible distance, it must have temporarily outshone hundreds of billions of normal stars combined. The variety of stars in Andromeda tells us about the galaxy's chemical evolution. The oldest stars, formed when the galaxy was young, contain almost no heavy elements. They're made almost entirely of hydrogen and helium, the primordial elements forged in the Big Bang. But subsequent generations of stars incorporated the heavier elements created in the cores of previous generations and scattered into space by supernova. Each generation of stars contains more carbon, oxygen, nitrogen, iron, and other elements essential for planets and life. The Sun, and indeed Earth, are made from material recycled through multiple generations of stars. We are quite literally made of star stuff. And the same is true throughout Andromeda. The planets orbiting stars there, if they exist, are made from the same periodic table, forged in the same stellar furnaces, governed by the same laws of physics. The distribution of elements varies across Andromeda. The central regions, where star formation occurred early and intensely, are metal-rich, using the astronomical definition of metal, which means any element heavier than helium. The outer regions, where star formation has been less active, are more metal-poor. By mapping this metallicity gradient, astronomers can reconstruct the galaxy's formation history, determining where and when different regions formed their stars. But perhaps the most intriguing aspect of Andromeda's stellar population is what it tells us about the galaxy's future. The star formation rate in Andromeda today is relatively modest, only about 1 solar mass per year. That means Andromeda is creating the equivalent of 1 sun-like star every year. By cosmic standards, this is actually quite sedate. Many galaxies, especially those involved in recent collisions, are forming stars hundreds or thousands of times faster. Andromeda is mature, settled, no longer in the fiery youth of rapid star formation. Most of its gas has already been converted into stars. The galaxy is slowly running out of fuel. But this peaceful middle age won't last. In about 4 to 5 billion years, maybe sooner, maybe later, Andromeda and the Milky Way will collide. When that happens, the gravitational interactions will compress gas clouds, triggering an intense burst of star formation, a starburst event that will light up both galaxies with the blue-white light of millions of newborn stars. The night sky will blaze with star formation. But that's a story for later. For now, Andromeda drifts through space, a galaxy in its prime, containing 1 trillion suns and secrets we're only beginning to uncover. At the heart of Andromeda, hidden within the bright nuclear star cluster, lurks a monster. A supermassive black hole containing approximately 100 to 140 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. This dark heart doesn't emit light itself. Nothing can escape its event horizon, not even light. But we know it's there. We can see its influence on the stars and gas around it, pulled into motion by gravity so intense it warps space and time itself. The black hole at Andromeda's centre, designated M31*, is roughly 25 to 35 times more massive than Sagittarius A*, the supermassive black hole at the centre of our own Milky Way. In fact, Andromeda's black hole is intermediate in mass between the Milky Way's relatively modest 4 million solar mass black hole and the true monsters found at the centres of giant elliptical galaxies, like the 6.5 billion solar mass behemoth in Messier 87, which was the first black hole ever directly imaged by the Event Horizon Telescope in 2019. Supermassive black holes are thought to reside at the centres of most, if not all, large galaxies. They form early in a galaxy's history, perhaps from the collapse of massive gas clouds or from the merger of many smaller black holes. Once formed, they grow by accreting material, swallowing gas, dust, and occasionally entire stars. Some supermassive black holes are extremely active, powering quasars and active galactic nuclei that outshine their entire host galaxies. Material falling into these active black holes forms an accretion disk, a swirling maelstrom of superheated gas that emits intense radiation across the electromagnetic spectrum. The most active black holes can consume the mass of the Sun every few years, or even faster. But Andromeda's black hole is remarkably quiet. It's not actively feeding. There's no bright accretion disk, no powerful jets of matter shooting out at near-light speed, no intense radiation output. M31* is, for all intents and purposes, sleeping. It sits dormant at the galaxy's centre, a vast gravitational well that pulls on surrounding stars but doesn't actively consume significant amounts of material. This quiescence is actually somewhat puzzling. With so much gas and stars nearby, why isn't the black hole feeding more actively? The answer seems to be in how material reaches the black hole. Gas and dust can't simply fall straight in. They have angular momentum rotational motion that keeps them in orbit rather than plunging directly into the black hole. To actually fall into the black hole, this angular momentum must be shed somehow, perhaps through interactions with other material or magnetic fields. In active black holes, gas settles into an accretion disk where friction and magnetic forces drain away the angular momentum, allowing material to spiral inward. But in Andromeda, this process seems to be highly inefficient. Recent observations using the Hubble Space Telescope and the Spitzer Space Telescope revealed how Andromeda's black hole feeds. Instead of a bright accretion disk, the feeding happens through long, thin filaments of gas and dust that spiral inward from considerable distances. These filaments are like cosmic spaghetti, thin streams of material slowly making their way toward the black hole. The process is gentle, almost delicate. Material arrives in small amounts, not in the massive torrents that power active galactic nuclei. This explains why Andromeda's black hole is so quiet. It's not starving. It's simply eating very slowly, savouring small meals rather than gorging on cosmic banquets. But the black hole isn't entirely dormant. X-ray observations with the Chandra X-ray Observatory have detected occasional flares from M31*, brief bursts of X-ray emission lasting hours to days. These flares occur when something, perhaps a gas cloud or a disrupted star, falls into the black hole more rapidly than usual. The material heats to millions of degrees as it accelerates toward the event horizon, emitting X-rays in a final scream before crossing the point of no return. Between 2000 and the present, Chandra has monitored Andromeda's centre continuously, building up a detailed light curve showing when these flares occur. 2 major flares were detected in 2006 and 2013, periods when the black hole's X-ray emission increased by factors of tens or hundreds. Interestingly, these flares coincided with detections of high-energy neutrinos by the IceCube Neutrino Observatory, ghostly subatomic particles that barely interact with matter and can pass through entire planets unimpeded. The correlation between X-ray flares and neutrino detection suggests that material falling into Andromeda's black hole can produce high-energy particles, not just electromagnetic radiation. This opens a new window into understanding the extreme physics near black hole event horizons. The hardness ratio of the X-rays from Andromeda's black hole, meaning the proportion of high-energy versus low-energy X-rays, is similar to the Milky Way's black hole when both are in their quiescent states. But during flares, Andromeda's X-rays are significantly softer, containing a greater proportion of low-energy photons. This difference hints at different flaring mechanisms in the 2 black holes, perhaps related to the magnetic field configurations around them or the composition of the infalling material. Understanding these differences requires more observations, more data, more pieces of the puzzle. One of the most peculiar features of Andromeda's nucleus is its double nucleus structure, discovered by Hubble in the 1990s. Instead of a single bright core centered on the galaxy's rotation, Hubble images showed 2 distinct concentrations of stars separated by about 5 light-years. One is slightly brighter than the other, and neither appeared to be perfectly centered on the galaxy's dynamical center. This was deeply puzzling. Galaxies shouldn't have double nuclei. What was going on? Further observations revealed the truth. The apparent double nucleus is actually an optical illusion created by a single eccentric disk of stars orbiting the central black hole. This disk is tilted and elongated, creating 2 bright peaks when viewed from our angle. The true center of the galaxy, where the black hole resides, corresponds to the fainter of the 2 peaks. The brighter peak is simply where the eccentric disk appears most prominent from Earth's perspective. It's a geometric effect, like seeing the 2 sides of a tilted ring and mistaking them for 2 separate objects. But why is there an eccentric disk at all? Stellar dynamics models suggest that the disk contains about 15 million solar masses of stars orbiting the black hole, at distances of 1 to 10 light-years. These stars are moving in a coherent pattern, all orbiting in roughly the same direction, but in an elongated, eccentric path rather than circular orbits. Such a configuration could result from a past galactic merger, if a smaller galaxy fell into Andromeda and its stars were captured into orbit around the central black hole. Alternatively, the eccentric disk might be a natural result of gravitational instabilities in the original gas disk that fed the black hole during the galaxy's formation. Whatever its origin, the eccentric disk is a reminder that galactic, nuclear, complex, dynamic environments. Stars don't simply orbit peacefully, they interact gravitationally, forming structures and patterns that evolve over millions of years. The disk we see today is a snapshot, a frozen moment in an ongoing process that will continue for as long as Andromeda exists. Looking ahead, Andromeda's black hole faces a dramatic future. When Andromeda and the Milky Way collide in about 4 to 5 billion years, their respective supermassive black holes will also eventually merge. This won't happen immediately. The collision of the galaxies will take hundreds of millions of years, with multiple close passes before the final merger. During each close approach, gas from both galaxies will be funneled toward the black holes, likely triggering intense accretion and transforming both quiet black holes into active galactic nuclei, at least temporarily. Eventually, billions of years after the collision begins, the two black holes will sink to the centre of the merged galaxy, forming a binary black hole system. They'll orbit each other, getting closer and closer as they emit gravitational waves, ripples in the fabric of space-time itself. These gravitational waves carry away energy and angular momentum, causing the black holes to spiral inward. Simulations suggest that it will take about 17 million years for the two black holes to merge completely, far faster than the billions of years required for the galaxies themselves to fully merge. When the black holes finally collide, the merger will be the most violent event in the local universe. Two black holes, one containing 100 to 140 million solar masses, the other containing 4 million solar masses, will crash together and merge into a single black hole of about 144 million solar masses. The merger will emit a massive burst of gravitational waves, sending ripples through space-time that will propagate throughout the universe. Unfortunately, instruments like LIGO, which detect gravitational waves from stellar mass black hole mergers, aren't sensitive to the low-frequency gravitational waves from supermassive black hole mergers. But future space-based detectors, like the planned LISA mission, will be able to detect such mergers from galaxies billions of light-years away. When our own local black hole merger occurs, it will be the strongest gravitational wave signal ever recorded, a cosmic event detectable across the entire observable universe. For now, though, Andromeda's black hole waits. It sits at the centre of the galaxy, a dark gravitational anchor slowly consuming thin filaments of gas, occasionally flaring when something substantial falls in, and quietly shaping the motions of millions of stars in the nuclear region. It's a sleeping giant, waiting for the cosmic collision that will wake it and transform it into one of the most powerful objects in the universe. But that's billions of years in the future. For now, it simply exists, 100 million solar mass void in space, invisible but undeniable, a secret at the heart of Andromeda. Andromeda's spiral arms are among its most beautiful and scientifically intriguing features. These elegant structures wind outward from the galactic core, traced by bright young stars and glowing nebula. But the arms aren't solid structures. They're not like the arms of a pinwheel, rigidly attached to the centre and rotating as a unit. Instead, they're density waves, regions where stars and gas are temporarily concentrated as they orbit through the galactic disk. Imagine a traffic jam on a highway. Cars enter the jam, slow down, spend some time in the congested zone, then exit and speed up again. The jam itself, the region of dense traffic, remains in roughly the same location, even though individual cars are constantly flowing through it. Spiral arms work the same way. They're cosmic traffic jams where stars and gas clouds slow down and bunch together. The arms themselves rotate around the galactic centre more slowly than the stars do, so stars are constantly entering the arms, spending some time there, then exiting and continuing their orbits. But unlike a highway traffic jam, which is just an annoying delay, a spiral arm is a site of creation. When gas clouds enter a spiral arm, they slow down and compress. This compression can trigger gravitational collapse, causing the clouds to fragment and form new stars. The most massive of these newborn stars are hot and blue, burning their hydrogen fuel at prodigious rates and emitting intense ultraviolet radiation. This UV light ionizes the surrounding hydrogen gas, causing it to glow with the characteristic red of hydrogen alpha emission. The result is spectacular regions, vast nebulae glowing pink and red, studded with brilliant blue stars. These HI regions can be enormous. The largest ones in Andromeda span hundreds or even thousands of light-years and contain enough gas to form hundreds of thousands of stars. They're visible even from 2.5 million light-years away, appearing as bright knots along the spiral arms in deep images. Some of the most prominent HRI regions in Andromeda have their own catalogue numbers and have been studied extensively. They're stellar nurseries on a scale that dwarfs anything in our own galactic neighbourhood. but the spiral arms contain more than just newborn stars and glowing gas. There are also dark lanes, shadows traced by dense dust that blocks the light of stars behind it. These dust lanes run along the inner edges of the spiral arms, marking where gas has been compressed to even higher densities. The dust is made of tiny particles, mostly carbon and silicon compounds, formed in the atmospheres of old stars and ejected into space. These microscopic grains, each smaller than the width of a human hair, absorb and scatter starlight, creating the dark silhouettes visible in images of Andromeda. The dust isn't just aesthetically interesting, it plays a crucial role in star formation. Dust grains shield the interior of molecular clouds from ultraviolet radiation, allowing the gas to cool to temperatures just a few degrees above absolute zero. At these frigid temperatures, hydrogen atoms can stick together to form molecular hydrogen, H2, the actual fuel for star formation. Without dust to protect it, the gas would remain atomic and too hot to collapse. Dust enables star formation. The very particles that obscure our view are essential for creating new generations of stars. Observations of Andromeda at infrared wavelengths, which can penetrate dust, reveal the hidden structure of these dust lanes. The Spitzer Space Telescope observed Andromeda extensively in the infrared, mapping the distribution of warm dust heated by young stars. The images show intricate structures, filaments, and clumps of dust threading through the spiral arms. In some regions, the dust forms ring-like structures, perhaps the result of past interactions with satellite galaxies or the effects of the galaxy's central bar on gas flows. Speaking of the bar, Andromeda is classified as a barred spiral galaxy. The bar is a linear structure of stars extending through the central regions of the galaxy, perpendicular to the spiral arms. Bars are common in spiral galaxies. Our own Milky Way has one. They form naturally from gravitational instabilities in the disk and play an important role in channeling gas toward the galactic centre, feeding the central black hole and triggering star formation in the nuclear region. Andromeda's bar isn't as prominent as those in some galaxies. It's relatively weak and difficult to see in optical images because it's largely obscured by the bright bulge. But it's there, and it influences the galaxy's structure. The bar affects how gas flows through the disk, creating resonances where material piles up. These resonances can trigger the formation of spiral arms and rings. Some of the peculiarities in Andromeda's spiral structure, the asymmetries and irregularities, may be the result of interactions between the bar and the disk. The exact number of spiral arms in Andromeda is debatable. Unlike some galaxies with clear, well-defined two-arm or four-arm patterns, Andromeda's arms are fragmented and asymmetric. Some regions show clear spiral structure, others are chaotic with broken arm segments and spurs jutting off at odd angles. This messiness is actually evidence of Andromeda's violent history. Galactic collisions and mergers disrupt the ordered spiral structure, creating irregularities and triggering off-axis star formation. One of the most peculiar features is the 10 kiloparsec ring, a roughly circular structure about 33,000 light-years in radius, centered on the galactic core. This ring shows up prominently in radio observations of neutral hydrogen gas and in studies of star-forming regions. It's a region of enhanced star formation, a cosmic assembly line producing new stars at a higher rate than the surrounding disk. The ring might be related to a resonance with the central bar, a location where gas naturally accumulates due to the orbital dynamics. Or it might be a relic of a past galactic collision, a wave of star formation triggered by the gravitational disturbance. Recent observations with radio telescopes have revealed another intriguing feature: ordered magnetic fields aligned along this 10 kiloparsec ring. Magnetic fields in galaxies are generated and amplified by dynamo processes, complex interactions between rotating gas and stellar motions. The strength and structure of these magnetic fields can influence star formation, controlling how gas collapses and how stellar winds and supernovae affect their surroundings. The fact that Andromeda's magnetic fields are ordered and aligned suggests some large-scale process organising them, perhaps related to the galaxy's rotation or to past interactions. The spiral arms are also home to open star clusters, loose groupings of dozens to hundreds of stars that form together from the same molecular cloud. These clusters drift through the disk, gradually dispersing over hundreds of millions of years as gravitational interactions eject members one by one. While they exist, open clusters are laboratories for studying stellar evolution, because all their members formed at the same time from the same material, differing only in mass. By observing clusters of different ages, astronomers can piece together how stars of different masses evolve. One of the most spectacular open clusters in Andromeda is located within NGC 206, the bright star cloud mentioned earlier. This region contains multiple overlapping clusters of young stars, all formed in a recent burst of star formation. The brightest stars are blue supergiants, massive stars that will live only a few million years before exploding as supernovae. Their intense light and powerful stellar winds sculpt the surrounding gas into elaborate shapes, creating bubbles and shells visible in high-resolution images. But not all of Andromeda's spiral arms are actively forming stars. Some regions are relatively quiescent, containing gas but little current star formation. This patchiness reflects the stochastic nature of star formation. It doesn't happen uniformly across the galaxy. It occurs in bursts triggered by specific conditions, perhaps the passage through a spiral arm, the collision of gas clouds, or the shock wave from a nearby supernova. Once a burst of star formation begins, it can be self-propagating. The UV radiation and stellar winds from the first generation of massive stars compress nearby gas, triggering the formation of the next generation. This sequential star formation can create expanding rings and shells of stars, visible in detailed images as associations of young stars spreading outward from a central region. The study of Andromeda's spiral arms and star-forming regions tells us not just about this one galaxy, but about the processes that govern star formation in all spiral galaxies. By observing Andromeda from the outside, we can see patterns and structures that are difficult or impossible to observe in our own Milky Way. We're embedded in our galaxy's disk, surrounded by dust and unable to get a big-picture view. Andromeda gives us that view. It's a laboratory just 2.5 million light-years away, close enough for detailed study but far enough that we can see the whole picture. Every new observation reveals more details, more structures, more clues to how galaxies build their stars and how those stars in turn shape the galaxies that made them. Beyond the visible disk of Andromeda, beyond the spiral arms and the bright star-forming regions, lies the halo, a vast, roughly spherical region extending far into intergalactic space. The halo is faint, populated by old stars and globular clusters, but it contains important clues about Andromeda's formation and evolution. And orbiting through the halo, like planets around a sun, are dozens of satellite galaxies, dwarf systems gravitationally bound to Andromeda. Andromeda has at least 36 known satellite galaxies, though the true number is likely higher. Many of these satellites are extremely faint dwarf spheroidal galaxies, systems containing only a few million stars spread across several hundred light-years. They're so faint that they're incredibly difficult to detect, visible only as slight overdensities of stars against the background. Some of Andromeda's satellites have only been discovered in the past decade or two, revealed by deep surveys searching for these ghostly systems. The brightest of Andromeda's satellites is Messier 32, designated M32, a compact elliptical galaxy visible in even small telescopes as a fuzzy patch near Andromeda's core. M32 is peculiar. It's far denser than most elliptical galaxies, packed with stars in a small volume. It also contains a surprising amount of young stars, despite being an elliptical galaxy that should be dominated by old stellar populations. These oddities have led astronomers to suspect that M32 isn't a pristine dwarf galaxy. It's the stripped core of a much larger galaxy that collided with Andromeda billions of years ago. This larger galaxy, now called M32P, meaning M32 progenitor, was once a massive spiral galaxy, possibly the third largest galaxy in the local group after Andromeda and the Milky Way. Around 2 billion years ago, M32P fell into Andromeda. The collision was catastrophic. Tidal forces from Andromeda's gravity ripped M32P apart, stripping away its outer stars and scattering them into Andromeda's halo. The collision also funneled gas into Andromeda's core, triggering an intense burst of star formation that created many of the young stars now seen in Andromeda's bulge. What remained of M32P is what we now see as M32, a dense remnant core containing the galaxy's original nucleus, and a fraction of its stars. The rest of M32P's stars were scattered into Andromeda's halo, where they now form a faint metal-rich stellar stream. By studying the chemical composition and orbits of halo stars, astronomers have been able to identify which stars came from M32P and reconstruct the details of this ancient collision. But M32P isn't the only galaxy Andromeda has consumed. Globular cluster studies reveal at least 2 major merger events in Andromeda's past. Globular clusters are useful tracers of galactic mergers because they're long-lived and retain memory of their original orbits. By measuring the motions and orbits of Andromeda's globular clusters, astronomers have identified 2 distinct groups. One group, containing older clusters, orbits perpendicular to Andromeda's disk. Another group, containing younger clusters, orbits at about a 90-degree angle to the first group. These 2 groups represent the remnants of 2 separate dwarf galaxies that Andromeda consumed, one about 2 to 3 billion years ago, the other nearly 10 billion years ago. The process of galactic cannibalism is a key part of galaxy evolution. In the current cosmological paradigm, called lambda cold dark matter, large galaxies like Andromeda are built hierarchically, assembling from smaller pieces over billions of years. Early in cosmic history, small dark matter halos collapsed and formed the first dwarf galaxies. These dwarfs merged together, forming larger galaxies, which merged to form even larger ones. The process continues to this day, with large galaxies like Andromeda still consuming smaller satellites. Each merger adds mass to the host galaxy and injects energy into the system, stirring up stars and gas. The disruption triggers star formation, creates tidal streams of stars stretched across space, and heats the stellar halo. The smooth distribution of halo stars we see today in Andromeda is the aggregate of all these past merger events. Each infalling dwarf galaxy was torn apart and its stars mixed into the halo, creating a well-blended population that's difficult to disentangle. But tidal streams are the exception. These are relatively recent merger events where the disrupted dwarf galaxy hasn't yet fully mixed. The stars still trace out the dwarf's original orbit, forming a stream that wraps around Andromeda like a ribbon. Several such streams have been discovered around Andromeda, ghostly trails marking where dwarf galaxies met their end. The streams can persist for billions of years before finally dispersing, making them valuable tools for reconstructing merger histories. One of the most spectacular tidal streams around Andromeda is the giant stellar stream, a faint arc of stars extending tens of thousands of light-years across the halo. This stream is thought to be a remnant of the M32P merger, the same event that created the compact remnant M32. Computer simulations of the M32P collision can reproduce the observed structure of the giant stellar stream, lending strong support to the idea that M32 and the stream share a common origin. Other streams are smaller and fainter, visible only in the deepest surveys. Some are mere wisps containing only a few thousand stars spread across vast regions. But each stream is a fossil record, preserving information about a long-dead galaxy and its final doom. By studying these streams, astronomers can determine when the merger occurred, what the original dwarf galaxy was like, and how the merger affected Andromeda. The satellite galaxies currently orbiting Andromeda are the survivors, the dwarfs that haven't yet been consumed. But they won't survive forever. Tidal forces from Andromeda are already affecting them, pulling on their outer stars and stripping away gas. Some of the satellites are being quenched, meaning their star formation is shutting down. Gas is being removed by ram pressure as the dwarf galaxies plough through Andromeda's hot halo gas, or by tidal stripping as Andromeda's gravity pulls the gas away. Without gas, the satellites can't form new stars. They become red and dead, populated entirely by old stars with no young blue stars to brighten them. Studies of Andromeda's satellites show that the quenching process begins long before the dwarf galaxies actually fall into Andromeda. Even satellites that haven't yet made their first close approach to Andromeda show signs of reduced star formation. This pre-processing suggests that the environment around Andromeda, not just close encounters with the galaxy itself, affects satellite galaxies. Perhaps the hot gas surrounding Andromeda, the circumgalactic medium, is already removing gas from the satellites, or perhaps tidal forces become significant at surprisingly large distances. Interestingly, Andromeda's satellite system shows some unusual properties. Many of the satellites seem to orbit in a vast thin plane, all moving in roughly the same direction. This plane of satellites is perpendicular to Andromeda's disk and extends far into the halo. The existence of this plane is puzzling. Random mergers and acquisitions shouldn't produce such an ordered structure. Some astronomers suggest that the satellites might have been accreted along filaments of the cosmic web, the large-scale structure of dark matter that threads through the universe. If multiple dwarf galaxies fell into Andromeda along the same cosmic filament, they might naturally end up in a plane. Alternatively, the plane might be a tidal feature, remnants of a single large merger that broke up into multiple pieces. Or it might be a statistical fluke, an apparent pattern that isn't actually significant. The jury is still out. What's clear is that Andromeda's satellite system is complex and doesn't fit simple models. The halo itself extends far beyond the visible satellites. Studies of individual halo stars show that Andromeda's stellar halo reaches out to at least 200,000 light-years from the galactic centre, possibly farther. The density of stars drops rapidly with distance, falling exponentially as you move outward. But even in the outermost reaches, there are stars, lonely ancient suns orbiting through the darkness, part of Andromeda yet separated from most of the galaxy by vast gulfs of empty space. These halo stars are metal poor, containing far fewer heavy elements than stars in the disk. This low metallicity indicates they formed early in the universe, when there hadn't yet been many generations of stars to enrich the interstellar medium with heavy elements. Many halo stars are more than 10 billion years old, among the oldest objects in Andromeda. They've been orbiting the galactic centre for most of cosmic history, witnesses to the galaxy's entire evolution. But the halo isn't completely metal poor. Some halo stars, particularly those associated with recent mergers like M32P, are quite metal-rich. This creates a complex picture, with multiple stellar populations of different ages and compositions coexisting in the halo. By carefully measuring the properties of individual halo stars, their metallicity, age, and kinematics, astronomers can assign them to different merger events, effectively reverse engineering Andromeda's assembly history. The dark matter halo extends even farther than the stellar halo, reaching hundreds of thousands of light-years into intergalactic space. This invisible scaffolding contains most of Andromeda's mass, and provides the gravitational framework within which the visible galaxy exists. The shape of the dark matter halo is uncertain. Some studies suggest it's oblate, flattened along the rotation axis. Others suggest it's more spherical. The uncertainty arises because dark matter is invisible. We must infer its distribution from its gravitational effects on visible matter, and those effects are subtle and difficult to measure precisely. What we can say is that the dark matter halo plays a crucial role in Andromeda's evolution. It provides the gravitational well that captures satellite galaxies, pulling them in and eventually tearing them apart. It affects the orbits of stars in the outer halo, determining whether they remain bound to the galaxy or escape into intergalactic space, and it will be crucial in the eventual merger with the Milky Way, as the two dark matter halos interact and eventually coalesce. Looking at Andromeda's halo and satellites gives us a view of galactic evolution in action. We're seeing the ongoing process of hierarchical assembly, watching in real time, or at least in real geological time, as a large galaxy grows by consuming smaller ones. The satellites we see today are the building blocks from which future generations of Andromeda's stars will be made. Billions of years from now, they'll have been torn apart and their stars scattered into the halo, joining the ghosts of galaxies past. It's a violent process, but it's how galaxies grow, how structure builds in the universe. Andromeda's halo is a graveyard and a construction site, a place where galaxies go to die and where larger galaxies are born. Andromeda has not grown peacefully. Its history is written in violence, in the wreckage of smaller galaxies consumed and scattered across its halo. This galactic cannibalism is a normal part of galaxy evolution, but Andromeda seems to have had a particularly active merger history, more so than our own Milky Way. The evidence is everywhere once you know where to look. The stellar streams wrapping around the galaxy, the metal-rich stars in the halo that shouldn't be there if Andromeda had evolved in isolation. The peculiar satellite galaxy M32, too dense and too young to be an ordinary dwarf elliptical. The disturbed structure of the disk, with asymmetric spiral arms and odd features that don't match models of pristine spiral galaxies. All of these are clues, forensic evidence of past collisions. Computer simulations have become powerful tools for reconstructing these ancient events. By inputting the properties of Andromeda today, its mass, rotation, stellar populations, and the observed positions and velocities of its satellite galaxies, astronomers can run time backward, essentially rewinding the cosmic movie to see what things looked like in the past. These simulations can test different merger scenarios, trying different masses, orbits, and timings for past collisions, and seeing which ones reproduce what we observe today. The simulations confirm that Andromeda merged with a massive galaxy, the aforementioned M32P, approximately 2 billion years ago. M32P was a giant containing perhaps 25 billion solar masses of stars, making it the third largest galaxy in the local group at the time. When M32P fell into Andromeda, the collision was spectacular. The two galaxies didn't merge immediately. Instead, they passed through each other, with M32P's stars and gas ploughing through Andromeda's disk. The gravitational interaction between the two galaxies stripped stars from M32P and flung them into elongated orbits. Gas from M32P was funneled toward Andromeda's centre, triggering an intense starburst that created billions of new stars. After the first passage, M32P swung back around for another encounter and another. With each passage, more of M32P was torn away. Eventually, after hundreds of millions of years and multiple pericenter passages, nothing remained of M32P except its dense core, what we now see as M32, and the scattered wreckage of its stars in Andromeda's halo. The giant stellar stream is a scar from this merger, a trail of stars marking M32P's death spiral. But the M32P merger isn't the only major event in Andromeda's past. The globular cluster studies mentioned earlier revealed evidence of at least one other significant merger event about 10 billion years ago, early in Andromeda's history. This ancient merger would have occurred when the universe was only a few billion years old, in the epoch of peak galaxy formation. The merger partner in this case was probably a dwarf galaxy, much less massive than M32P, but still significant enough to leave traces in the globular cluster population. These major mergers would have profoundly affected Andromeda's evolution. Each collision injected energy into the system, heating the stellar disk and thickening it. Gas was stirred up and compressed, triggering bursts of star formation. The distribution of dark matter was altered, as the infalling galaxy brought its own dark matter halo with it. The galaxy we see today is the product of all these events, accumulated history of growth by consumption. But mergers aren't just about growth, they also disrupt. Andromeda's disk shows evidence of disturbances that can't be explained by smooth, isolated evolution. The spiral arms are asymmetric. The distribution of neutral hydrogen gas is offset from the stellar disk by several thousand light-years in some regions. There are peculiar velocities, stars moving in ways that don't fit the expected rotation pattern. All of these suggest that something has stirred up the disk relatively recently, astronomically speaking. The likely culprit is M32 itself. Computer simulations show that M32, the compact remnant of M32P, is still interacting with Andromeda. Its orbit takes it through Andromeda's disk every few 100 million years. Each passage creates a gravitational ripple, like a stone dropped in a pond. These ripples propagate through the disk, distorting the spiral structure and creating the asymmetries we observe. M32 is like a cosmic wrecking ball, unable to significantly damage Andromeda anymore but still causing disruptions with each passage. Another smoking gun for past mergers is the chemical composition of stars in different regions of Andromeda. Stars in the disk have a characteristic metallicity that reflects the history of star formation there. Stars in the bulge have different metallicities, typically higher because star formation in the bulge occurred early and intensely, rapidly enriching the gas with heavy elements. But stars in the halo show a huge range of metallicities, from extremely metal-poor stars that formed early in the universe to metal-rich stars that shouldn't be in the halo at all. These metal-rich halo stars are the smoking gun. They didn't form in the halo, they formed in the disk of an infalling galaxy and were stripped away during a merger, scattered into Andromeda's halo where they don't belong. By mapping the distribution and properties of these metal-rich halo stars, astronomers can trace which regions of the halo came from which merger event. It's like archaeological stratigraphy, identifying different layers of deposition. The comparison between Andromeda and the Milky Way is instructive. Both are large spiral galaxies of similar mass and age. Both have had merger events in their pasts, but Andromeda's merger history appears to be more violent and more recent. The Milky Way shows evidence of consuming the Gaia Enceladus sausage dwarf galaxy about 10 billion years ago, and it's currently in the process of tidally disrupting the Sagittarius dwarf spheroidal galaxy. But these are relatively small events compared to the M32P merger. Andromeda seems to have had a more eventful life, more major mergers that have left clear signatures in its structure and stellar populations. This difference might be partly due to their different environments within the local group. Andromeda is the dominant galaxy, the most massive system in the local group. It has a larger sphere of influence and has accreted more satellite galaxies. The Milky Way, while comparable in mass, has had less material to work with in its immediate vicinity. Or perhaps we've simply detected more merger events in Andromeda because we can observe it from the outside, seeing structures and patterns that would be difficult to detect from our embedded position within the Milky Way. Whatever the reasons, Andromeda's violent past is written in its present structure. Every asymmetry, every stellar stream, every peculiar velocity is a clue. Astronomers are cosmic detectives piecing together the history of galaxies from the evidence they left behind, and Andromeda, with its rich merger history and proximity that allows detailed study, is one of the best case studies we have. By understanding Andromeda's past, we gain insight into how all galaxies grow and evolve, building themselves up through billions of years of galactic cannibalism. One of the greatest mysteries in modern astronomy is the nature of dark matter, and Andromeda is one of our best laboratories for studying it. The galaxy's rotation curve, the graph showing how fast stars and gas orbit as a function of distance from the centre, reveals the presence of vast amounts of unseen mass. In a simple universe with only visible matter, orbital velocities should decrease with distance from the galactic centre, just as planets farther from the Sun orbit more slowly than inner planets. This is basic Newtonian physics. The gravitational force falls off with distance, so objects farther out should move more slowly. But that's not what we observe. When astronomers measure the rotation curve of Andromeda, they find that the velocities don't decrease in the outer regions. Instead, the curve flattens out. Stars and gas in the outer disk are moving just as fast as material closer in, sometimes even faster. This flat rotation curve is the signature of dark matter. To explain the high velocities in the outer galaxy, there must be additional mass, beyond what we can see in stars and gas, providing extra gravitational pull. This unseen mass is dark matter, and it must be distributed in a large halo surrounding the visible galaxy. The exact distribution can be inferred from the shape of the rotation curve. Different dark matter profiles produce different rotation curves, so by carefully measuring the rotation curve and comparing it to models, astronomers can constrain the dark matter distribution. Several dark matter profiles have been proposed and tested against Andromeda's rotation curve. The Navarro-Frank-White profile, or NFW profile, is a theoretical prediction from cosmological simulations of dark matter halo formation. It predicts a specific density profile that increases steeply toward the centre and falls off gradually in the outer regions. The Hernquist profile is similar but with slightly different mathematics. The Einasto profile is more flexible, with an adjustable shape parameter, and the isothermal profile is a simpler model often used for analytical calculations. Studies comparing these profiles to Andromeda's rotation curve data show that the NFW and Hernquist profiles fit the data reasonably well, while the Einasto profile provides a poorer fit. This suggests that Andromeda's dark matter halo is consistent with predictions from cold dark matter simulations, supporting the standard cosmological model. But the fits aren't perfect. There are discrepancies in the inner regions where the predicted dark matter density might be higher than what the rotation curve suggests. This has led to discussions about whether real dark matter halos match the idealized predictions from simulations. One possibility is that baryonic physics, the behavior of normal matter, affects the dark matter distribution. When gas cools and forms stars, it releases energy through supernova explosions and stellar winds. This energy can heat gas and drive it out of the galaxy, a process called feedback. Feedback can redistribute mass in the galaxy, flattening the central density profile of dark matter. Some simulations, including detailed baryonic physics, produce dark matter halos with shallower central densities than pure dark matter simulations, better matching the observations. Another intriguing finding is that Andromeda's dark matter halo may not be spherical. Studies using the thickness of the neutral hydrogen gas disk as a constraint suggest that the dark matter halo is oblate, flattened along the rotation axis. This is interesting because simulations often predict triaxial or prolate halos, elongated along one or two axes rather than flattened. If Andromeda's halo is indeed oblate, it might be the result of its formation history, shaped by the specific pattern of mergers it experienced. The virial mass of Andromeda's dark matter halo, meaning the total mass within the virial radius where the halo is in approximate equilibrium, is estimated at 800 billion to 1.1 trillion solar masses. The virial radius, called R200, is about 190 to 210 kiloparsecs, roughly 620,000 to 685,000 light-years. This is enormous, extending far beyond the visible galaxy. Most of Andromeda's mass is dark matter, with visible stars and gas making up perhaps 10 to 20% of the total. Within the central regions of the galaxy, the dark matter density is particularly high. For the Einasto profile, studies estimate the average dark matter density within the central 10 parsecs, about 33 light-years, to be 16 to 61 solar masses per cubic parsec. In units more familiar to particle physics, this translates to about 0.6 to 2.3 tera-electron volts per cubic centimetre. This is relevant for dark matter detection experiments, which are trying to observe interactions between dark matter particles and normal matter. The higher the local dark matter density, the more likely such interactions are to occur. Interestingly, the central dark matter density in Andromeda is comparable to densities found in nearby dwarf galaxies, low-surface brightness galaxies, and even distant massive galaxies. This suggests that the physical processes regulating central dark matter density, perhaps feedback from star formation and supernovae, operate similarly across a wide range of galaxy masses and environments. It's a hint that there might be universal mechanisms at play, linking the evolution of dark matter and baryonic matter. But despite all we've learned, fundamental questions remain. We still don't know what dark matter is. Is it made of weakly interacting massive particles or WIMPs, as many physicists suspect? Is it axions, hypothetical particles far lighter than any known particle? Is it primordial black holes, remnants from the early universe? Or is it something entirely different, something we haven't thought of yet? Experiments are searching for dark matter particles, trying to detect them directly, or produce them in particle accelerators. So far, these experiments have come up empty. Dark matter remains elusive, detectable only through its gravitational effects. There's also the possibility, considered by some physicists, that dark matter doesn't exist at all. Perhaps our understanding of gravity is wrong. Modified Newtonian dynamics, or MOND, proposes that gravity behaves differently at very low accelerations, like those in the outer regions of galaxies. MOND can reproduce flat rotation curves without invoking dark matter. But MOND struggles to explain other observations like gravitational lensing and the cosmic microwave background. Most physicists favour dark matter as the explanation, but MOND remains an alternative that can't be entirely ruled out. Andromeda's role in this cosmic mystery is crucial. Its proximity allows detailed measurements that aren't possible for more distant galaxies. By carefully mapping the rotation curve, studying the kinematics of halo stars, and measuring the motions of satellite galaxies, astronomers can constrain the dark matter distribution with precision unavailable elsewhere. Every new data point, every improved measurement, brings us closer to understanding this invisible component that dominates the mass of the universe. And when Andromeda and the Milky Way collide, the interaction between their dark matter halos will be another key piece of evidence. Simulations predict specific behaviours for how dark matter halos should merge. Observations of the collision, if we could somehow observe it from the outside, would test those predictions. Of course, we won't be around to see it. But the collision will leave signatures in the merged galaxy structure that future civilizations, if they exist, could study. Andromeda isn't just helping us understand dark matter today. It's part of a cosmic experiment that will continue billions of years into the future. Perhaps the most dramatic chapter in Andromeda's story is yet to be written. The galaxy we see tonight, that faint smudge in the autumn sky, is hurtling toward us at about 110 kilometers per second. That's roughly 68 miles per second, or about 250,000 miles per hour. Andromeda is approaching, and in about 4 to 5 billion years, maybe a bit sooner or maybe later depending on the exact dynamics, it will arrive. The collision of Andromeda and the Milky Way will be the defining event in our cosmic neighbourhood for the next 10 billion years. For most of the 20th century, astronomers knew Andromeda was approaching based on its blue shift, the Doppler shift of its light towards shorter wavelengths indicating motion toward us. But knowing that Andromeda was approaching didn't tell the whole story. Was it heading straight for us, destined for a head-on collision? Or was it moving sideways as well, perhaps set to pass by at a safe distance? The answer required measuring Andromeda's tangential motion, its motion across our line of sight. This is incredibly difficult for an object so far away. Even at 250,000 miles per hour, Andromeda's motion across the sky is painfully slow from our perspective. The Hubble Space Telescope provided the answer in 2012. Over a period of several years, Hubble measured the positions of stars in Andromeda's halo with extreme precision, tracking how they moved against the background of even more distant galaxies billions of light-years away. These measurements revealed Andromeda's tangential motion, the verdict, a direct collision. Andromeda isn't going to pass by, it's coming straight for us. However, in 2025, a study published in Nature Astronomy threw some uncertainty into the picture. When researchers included the gravitational effects of other nearby galaxies, particularly the Large Magellanic Cloud, which is falling into the Milky Way, and the Triangulum Galaxy, the third largest member of the local group, the picture became more complicated. These additional gravitational pulls affect both the Milky Way's and Andromeda's motions. The new analysis suggested that there's roughly a 50% chance that Andromeda and the Milky Way won't collide at all over the next 10 billion years. They might pass by each other, their paths perturbed by the gravitational influences of other galaxies. So the collision might not happen, or it might. The uncertainties are large. What we can say is that Andromeda and the Milky Way are gravitationally bound, part of the same group of galaxies, and they will interact. Whether that interaction is a direct collision or a near miss followed by a later merger is still being determined. For the purposes of this discussion, let's assume the traditional scenario, a head-on collision in about 4 to 5 billion years, because that's the most studied and dramatic outcome. Assuming the collision occurs, here's what we expect based on computer simulations. The first signs will appear about 2 billion years from now. Andromeda will have grown noticeably larger in the night sky, no longer a faint smudge but a clear spiral structure visible to the naked eye. Over the next billion years it will continue to grow, becoming more and more prominent. By 3.75 billion years from now, Andromeda will fill a significant portion of the sky, a vast pinwheel of stars stretching from horizon to horizon in some directions. At 385 billion years from now, the galaxies will make their first close approach. Gas from both galaxies will collide, compressing and heating. The collision won't be gentle. When gas clouds moving at hundreds of kilometers per second slam together, they create shock waves that compress the gas to enormous densities and temperatures. This compression triggers intense star formation, a starburst event that will light up both galaxies with the blue-white light of millions of newborn massive stars. The night sky will be ablaze with star formation, vast nebulae glowing in reds and blues, countless new stars igniting across both galaxies. But individual stars won't collide. The distances between stars are so vast compared to their sizes that the probability of two stars actually hitting each other is negligible. Stars will pass through the space occupied by the other galaxy like ghosts, unaffected except by the overall gravitational field. Our Sun, if it still exists, will likely not collide with any star from Andromeda. However, its orbit will be perturbed. Simulations suggest about a 50% chance that the solar system will be flung farther out from the galactic centre, perhaps to the outer fringes of the merged galaxy. There's also about a 12% chance that the solar system will be ejected entirely, cast out into intergalactic space, orphaned from both parent galaxies. After the first close approach, the galaxies will pass through each other and swing back around for another encounter, and another. Each passage will further disrupt both galaxies, flinging stars into elongated orbits and triggering more bursts of star formation. At 4 billion years from now, Andromeda will appear stretched and warped by tidal forces. The Milky Way will also be distorted, its spiral structure in tatters, both galaxies locked in a cosmic embrace that's tearing them apart even as it brings them together. By 5.1 billion years from now, the cores of the two galaxies will appear as a pair of bright lobes in the sky, two centres of light where once there were separate galaxies. The merger is well underway. Gas and dust have been largely consumed in previous bursts of star formation, or blown away by stellar winds and supernovae. Star formation is slowing down, the fuel mostly exhausted. By 7 billion years from now, the merger is complete. The two galaxies have coalesced into a single, giant elliptical galaxy. The new galaxy, sometimes nicknamed Milkomeda or Milkdromeda, will be roughly spherical, lacking the spiral structure of its parent galaxies. It will be dominated by older yellowish stars. The bright blue stars from the starburst events will have long since exploded as supernovae or evolved into red giants. The galaxy will be a massive quiescent elliptical, its bright core dominating the sky of any planets that remain. But not all aspects of the merger will be visible. The dark matter halos of both galaxies will also merge, coalescing into a single larger dark matter halo. This process will occur over the same timescale as the stellar merger, with the two halos interpenetrating and mixing. Because dark matter doesn't collide or interact electromagnetically, it will simply pass through itself, mixing together in a complex dance governed purely by gravity. The supermassive black holes at the centres of both galaxies will also merge, but on a different timescale. Initially, as the two galaxies collide, the black holes will remain at the centres of their respective stellar cores, but as the cores sink toward the centre of the merged galaxy, the black holes will be dragged along. Eventually, they'll form a binary system orbiting each other at the heart of the new galaxy. This binary won't last forever. Interactions with surrounding stars will remove energy and angular momentum from the binary, causing the black holes to spiral inward. And as they get closer, they'll begin emitting gravitational waves, ripples in space-time that carry away energy. The closer they get, the faster they emit gravitational waves, and the faster they spiral inward. Eventually, about 17 million years after forming a binary, the two black holes will merge in a cataclysmic event that will send a massive pulse of gravitational waves throughout the universe. Of course, we won't be there to see any of this. Long before the collision occurs, the Sun will have exhausted the hydrogen in its core and begun swelling into a red giant. In about 1 to 2 billion years, the Sun's increasing luminosity will have created a runaway greenhouse effect on Earth, boiling away the oceans and making the planet uninhabitable. By the time Andromeda arrives, Earth will be a scorched, lifeless rock, if it exists at all. The Sun itself will likely still be around, possibly as a white dwarf if it has already completed its red giant phase, or possibly still as a red giant. But life on Earth will be long gone. However, if humanity or its descendants have become spacefaring and spread throughout the solar system or beyond, they might witness the spectacular show. The night sky transforming over millions of years, Andromeda growing from a faint smudge to a vast spiral dominating the heavens, then merging with our galaxy in a blaze of star formation before settling into a quiescent elliptical. It would be the most dramatic cosmic event visible from our corner of the universe, a once-in-a-galaxy lifetime spectacle. Astronomers continue to refine their predictions, running ever more detailed simulations that include not just the dark matter and stars but also gas dynamics, magnetic fields, black hole feedback, and the effects of individual stars. Each new simulation brings us closer to understanding exactly what will happen when Andromeda arrives. It won't be a catastrophe. Despite the violence of the collision on galactic scales for individual star systems, it will be mostly unremarkable. But it will reshape our cosmic landscape, ending the era of two large spiral galaxies in the local group and beginning a new era dominated by a single massive elliptical. The story of Andromeda is continuously being rewritten as new observations are made and new technologies come online. Just in January 2025, NASA released the most comprehensive image of Andromeda ever assembled, a mosaic created from over 600 separate Hubble Space Telescope observations taken over more than a decade. This image, containing 2.5 billion pixels, resolves approximately 200 million individual stars in Andromeda, providing an unprecedented view of our neighbouring galaxy. The mosaic is the result of two major Hubble programs, the Panchromatic Hubble Andromeda Treasury, or PHAT, which imaged the northern half of the galaxy, and the Panchromatic Hubble Andromeda Southern Treasury, or PAST, which completed the southern half. Together, these programs represent more than 1,000 Hubble orbits, an enormous investment of time on one of the most valuable astronomical instruments ever built. What does the image reveal? Everything. It shows individual stars of all types, from brilliant blue supergiants to faint red dwarfs. It shows open clusters, dense knots of young stars. It shows dark dust lanes snaking through the spiral arms. It shows globular clusters in the halo, ancient spheres of stars orbiting the galaxy. It shows the satellite galaxy M32, a compact elliptical hugging close to Andromeda's core. It shows NGC 206, the most prominent star cloud in Andromeda, a region of intense recent star formation. It shows background galaxies billions of light years beyond Andromeda, tiny smudges barely distinguishable from foreground stars. The detail is staggering. Zooming into any region of the image reveals structures invisible in ground-based photographs. Here's a cluster of newborn blue stars, each one many times more massive than the Sun. There's a shell of gas blown out by a supernova, expanding through space at thousands of kilometers per second. Over there, a dark globule of dust where future stars are gestating. Invisible cocoons hiding stellar embryos. Everywhere you look, there's something happening. Stars being born, stars dying, matter in constant motion. The image has already led to new discoveries. By measuring the colours and brightnesses of individual stars, astronomers can determine their ages and masses. Plotting these properties for millions of stars allows the construction of detailed star formation histories, showing when different regions of Andromeda formed their stars. The results show that Andromeda has a more active recent star formation history than the Milky Way, with more young stars and more evidence of ongoing star formation. This supports the idea that Andromeda has had a more eventful merger history, with recent collisions triggering bursts of star formation. The image also reveals the complexity of Andromeda's stellar populations. Different regions have different mixtures of star types, reflecting different formation histories. The bulge is dominated by old, metal-rich stars. The disk contains a mix of young and old stars. The halo is populated mostly by old, metal-poor stars, but with significant contamination from metal-rich stars stripped from infalling satellites. Mapping these populations across the galaxy allows astronomers to piece together the sequence of events that built Andromeda. Beyond Hubble's optical observations, other telescopes have provided complementary views. The Spitzer Space Telescope, observing in the infrared, mapped Andromeda's dust and revealed hidden star-forming regions obscured in optical light. The Chandra X-ray Observatory has monitored Andromeda's central black hole for over 2 decades, tracking its flares and X-ray emission. Radio telescopes have mapped neutral hydrogen gas and magnetic fields. The combined data from all these telescopes creates a multi-wavelength portrait, each wavelength revealing different aspects of the galaxy. One of the most exciting recent findings involves Andromeda's satellite galaxies. A comprehensive Hubble survey measured the motions of 36 known satellite galaxies, building a 3D map of their orbits around Andromeda. This allowed astronomers to rewind time and reconstruct where these satellites have been and where they're going. The results show that many of the satellites have been captured relatively recently and are still falling into Andromeda for the first time. Others have already made multiple passages and are in the process of being tidally stripped. The satellite survey also revealed how satellite quenching works. When a dwarf galaxy falls into a larger galaxy, it loses its gas and stops forming stars. The Hubble data shows that this quenching process depends on the satellite's mass and how close it gets to Andromeda. More massive satellites can retain their gas longer. Satellites that pass very close to Andromeda are stripped more rapidly. By studying these satellites, astronomers gain insight into the physics of galaxy interactions, information that's applicable to satellite galaxies around any large galaxy, including our own. Another recent discovery involves the circumgalactic medium, the vast halo of hot, diffuse gas surrounding Andromeda. This gas is extremely faint and difficult to detect, but observations with the Hubble Space Telescope using a technique called absorption line spectroscopy have mapped its extent. The technique works by looking at background quasars, distant bright objects whose light passes through Andromeda's halo on its way to us. The gas in the halo absorbs specific wavelengths of light from the quasar, creating absorption lines in the spectrum. By studying these absorption lines in the light from many quasars at different positions around Andromeda, astronomers can map the distribution and properties of the circumgalactic medium. The results show that Andromeda's circumgalactic medium extends at least 1.3 million light-years from the galaxy's centre, far beyond the visible stellar disk. This means Andromeda's and the Milky Way's circumgalactic media are already overlapping. We're already inside Andromeda's halo, and Andromeda is inside ours. The two galaxies are, in a sense, already beginning to interact through their extended gas halos. The collision has technically already begun. Looking to the future, new telescopes will continue to unveil Andromeda's secrets. The James Webb Space Telescope, with its infrared capabilities, can peer through dust to see star-forming regions in unprecedented detail. Webb can also observe cooler stars and brown dwarfs, filling in the sensors of Andromeda's low-mass stellar population. The upcoming Nancy Grace Roman Space Telescope will have a field of view 100 times larger than Hubble's, allowing it to map Andromeda's entire disk and halo in single exposures, and ground-based telescopes equipped with adaptive optics can now rival Hubble's resolution from the ground, providing complementary observations and spectroscopy of individual stars. Each new observation, each new data point adds to our understanding. Andromeda is the most studied galaxy beyond our own. It's a cosmic laboratory, a test case for theories of galaxy formation and evolution. Everything we learn about Andromeda teaches us something about galaxies in general, including our own Milky Way. And because Andromeda is our future collision partner, understanding it is understanding our own future, the destiny of our cosmic neighbourhood billions of years hence. So there you have it, the real secrets of the Andromeda Galaxy, a vast spiral of 1 trillion stars lying 2.5 million light-years across the cosmic void. A galaxy with a violent past built through galactic cannibalism, the consumption of dozens of smaller galaxies whose stars now populate its halo. A galaxy with a supermassive black hole at its heart, 100 million solar mass monster that occasionally flares but mostly sleeps. A galaxy surrounded by an invisible dark matter halo that dominates its mass and shapes its evolution. A galaxy hurtling toward us at 250,000 miles per hour, destined to collide with our own Milky Way in the distant future. Andromeda is more than just a faint smudge in the autumn sky. It's a monument to cosmic violence and cosmic beauty, to the patient assembly of galaxies over billions of years, to the ongoing drama of star birth and death playing out across hundreds of thousands of light years. It's a reminder that we live in a dynamic universe, where nothing is static, where even galaxies are in motion, colliding and merging on timescales almost too vast to comprehend. The next time you're out on a clear autumn night, far from city lights, take a moment to find Andromeda. Look northeast from the Great Square of Pegasus, find that faint elongated blur, and remember that you're seeing light that left that galaxy 2.5 million years ago. You're looking back in time, seeing Andromeda as it was in the deep past. And you're looking at our future collision partner, the galaxy that will one day merge with ours, transforming both in the process. Andromeda is a cosmic mirror showing us what our own galaxy might look like from the outside. It's a laboratory, where we can study processes too complex to observe in our own embedded position within the Milky Way. It's a destination, a future home for the merger product of two great spiral galaxies. And it's a mystery, still full of secrets waiting to be discovered by the next generation of telescopes and the next generation of astronomers. If you enjoyed this journey through the secrets of Andromeda, please take a moment to like this video and subscribe to the channel. Leave a comment letting me know what you'd like to explore next. The universe is vast and full of wonders, and there are countless stories still to tell. Thank you for joining me tonight. Good night.